Hi there. This video series is to display my problem solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 23rd Project Euler problem from start to finish, vocalizing my thought process throughout. As always, I will link to both Project Euler and my repository in the description. Let's dive in. Non-abundant sums. A perfect number is a number for which the sum of its proper divisors is exactly equal to the number. For example, the sum of the proper divisors of 28 would be 28, which means that 28 is a perfect number. A number n is called deficient if the sum of its proper divisors is less than n, and it is called abundant if the sum exceeds n. As 12 is the smallest abundant number, the smallest number that can be written as the sum of two abundant numbers is 24. By mathematical analysis, it can be shown that all integers greater than 28,123 can be written as the sum of two abundant numbers. However, this upper limit cannot be reduced any further by analysis, even though it is known that the greatest number that cannot be expressed as the sum of two abundant numbers is less than this limit. Find the sum of all of the positive integers which cannot be written as the sum of two abundant numbers. Okay, so we're going to copy over this problem statement. And this is actually pretty similar to a problem that was very, very recent. Yeah. Which is problem 21. So we're going to go ahead and copy this sum of divisors method. As you may recall if you've seen that video, this isn't the absolute most efficient way of doing this, but we only go up to the square root, so it's relatively efficient. And it's very close to the most efficient way of doing this. And let's go ahead and have our limit is equal to that. I'm going to go ahead and set it to equal to 124. No, 123. I'm not sure whether 28,000, from the wording of the question, I'm not sure whether 28,123 can be written as the sum of two abundant numbers or not. It sounds like all integers that are larger than that can be, but whether that number itself can be or not is an open question, at least in my opinion. So we want the sum of all the positive integers which cannot be written as the sum of two abundant numbers. Okay, so here's my thought as a general approach. First, find all the abundant numbers below this 28,123. Technically, we want to have to go all of the way up, but so first, find all abundant numbers. Next, find all numbers less than limit, which are sums of abundant numbers. Then we are going to find all of the numbers that aren't on that list and add them all together. So, first, find all abundant numbers. So, I'm just going to call this list abundance. And we are going to say for I in, let's say, range of 12 to limit plus 1. And this is going to end up being pretty similar. So the reason I'm starting at 12 is because the problem did already give us the answer that that is the smallest abundant number. I could just as easily throw it in here and start with 13. But just as a, like... yeah, and I'm going to let this 28,123 number be the biggest number that we look at for whether it's an abundant number or not. Let's see. I'm actually going to make this n instead of I, because that's what I did in problem 23. So I'm going to get the divisor sum is to find sum of divisors. And actually... let's see. So previously the problem was to evaluate the sum of all the amicable numbers. So we're going to have a somewhat different strategy now. And instead of having a divisor sum, we can just say if find sum of all divisors of n is equal to, or is greater than n, rather, then abundance dot append n, and then we will have all of our abundant numbers, which is not likely to be very many, but we'll see. And then I'm gonna say for I in range length of abundance, and then for j in range length of abundance. Actually, instead of just that, I'm going to say I plus 1. So, every single pair, right? So... sums of abundance is going to be our next list. And then what we're going to do is... I'm just going to say A equals abundance at index I, B... Do I need to pull these out into variables? No. But I feel like it makes things just slightly more readable. And it's going to save us some typing. So if A plus B is less than or equal to limit sums of abundance dot append A plus B. Actually, I could just do that. Sums of abundance dot if not a in sums of abundance, and it is less than the limit, then we want to add it. Just adding this little condition because again, just to make our lives a tiny bit easier. And obviously this is introducing an O of n squared complexity into this, and it's like the second step out of 3. So is this going to end up being the most efficient algorithm? No. But I am willing to bet that it is going to be efficient enough to make that minute time limit that we have from Project Euler. And then finally we have our sums equals 0, and that is the number that we want to print. I personally actually kind of want to print these other things as well, just for the sake of curiosity. But so far as like actually and then I'm just going to say for x in range for this one. And again, here we want to start with 1 and go to limit plus 1, because otherwise we won't actually look at this number. Maybe it makes sense to do that as a 4 and have this be limit and less than limit and stuff, but this also works. F not x in sums of abundance, non-abundant sums, plus equals x. And that's actually it. That's the entire code. So let's go ahead and run that, see if we've managed to succeed on try number 1, or if we run into an issue. So obviously we get our first list quite quickly. That is our list of abundance. I probably should have labeled that. And it is taking us a long time to go through all of these pairs. Which does in fact make sense given the sheer amount of abundance that we have here. Okay, so if 28,122 is an abundant number, okay. I think that I might stop this because it's already taken too long. Let's see, when did we start? 2057? Yeah, it's already taken over a minute. So let's go ahead and cancel that. And I'm going to change this to just the length of the abundance array. And then this O squared is taking a lot longer than I'm used to things taking in Python, and I'm kind of wondering if it's because we're doing something like this. I have a feeling we don't actually need this check, because if it's in there twice, it does not matter. So let's try removing that check, see if that gets us through that a little bit faster. Okay, so we have 6,965 abundant numbers. Now we're printing out all of the sums of abundance. This is going to take a little bit. Okay, so obviously printing out the sums of abundance on its own is making us is gonna make us fail. And also, actually, I just realized there's a bug here, because what's our earliest number that's sums of abundance? 12 plus 12, so 24. And we've actually got our code written here in a way that will not find that. So I think that we don't need to go through. So like this will do the first one plus itself, and then plus L after it, and then the second one plus itself plus all of the ones after it. So I think that gives us a more accurate list. And what I'm going to do here is I'm actually going to say, just give me the last 10 of those. So that it doesn't print out all of them again. My guess is that... And actually, I'm going to go ahead and print the length of that again. Kind of these last few that are sums of abundance are also... there's definitely some duplicates in here. Like, see, there's 28,122 is in here twice. Not sure of a great way to remove all of those duplicates, but it looks like this is actually quite extensive as well. So let's go ahead and cancel this. I'm going to call sums of abundance.sort. That might take a little bit, depending on how long that array is. But I think that it will make this go a lot faster, and it seems like we need just a teensy bit more speed here. So let's see. Okay, so obviously it's now taking much less time going through going through this step than it was previously. Let's see. And then it's still taking quite a long time going through this one. So I would say this is obviously not quite efficient enough yet. Again, I think it's this that's making us take a long time. So let's see. What can we do here? say for num in sums of abundance. Okay, so obviously there's way too many numbers, and I'm not sure of a great way in Python to make it, like, get rid of all of those numbers, other than maybe creating a dictionary. There probably are lots of great ways to accomplish just making that without any duplicates. But what I'm thinking that we should do is, instead of having this not x in sums of abundance check, just say for index value in enumerate sums of abundance. And we're going to have let's say start equals value if value greater than 0, else 0, or else 1. We want to start at 1 for the first one. And then end equals value if value less than the length of our sums of abundance, else limit plus 1. And what we're going to do is start in the range. Oh, this is a little bit too complicated, actually, or a little bit not complex enough. So what we actually want is start equals 1, end equals limit plus 1. And then if value is greater than 0, we want start equal to value and end equal to or actually if value less than the length of sums of abundance, we actually want end to equal sums of abundance at index plus 1. So basically, when we first come in here, let's see, maybe we do this a different way. Let's default this to some. So for the very first one, we actually want it to be sums of abundance at index. So let's see, if value equals 0, end equals sums of abundance, index plus 1. Else, if value is greater than 0, oh, not value, actually. We want this to be index. If index equals 0, okay. And index is less than the length of the sums of abundance minus 1. So basically, if the index is 0, we're on the first element. And we want the end to be literally just that. If the index is greater than 0, but we're not yet to the last element, we want to start at value and end at sums of abundance index plus 1. And then we'll default the end value to that limit plus 1 for when we are in the case of that very last element. And this code might not be super clear, I feel like, but I think it will at least get us started. And then, yeah, because of how this is set up, we start at 1. The end will be 24 is going to be our first number. Start and end are going to be equal for a lot of these, so we're just going to skip them. And then we don't need... Let's see. Actually, I'm going to say value plus 1. And the logic behind that is when we get to the value, we don't want to count it if it is inside of the sums of abundance. So, come in, very first element is equal to 24. We're going to start at 1 and go through 23. Add in those to our non-abundant sums. Our end is going to equal that 24. So let's actually be this end equals value. Then this should be what we need to do. This should give us the correct answer, if I have thought through this correctly. And obviously the previous algorithm has taken more than 10 minutes already. So, let's see. Again, very, very quick through that first step. Still pretty quick through that second step. And then this third step is the one that's slower. But there we go. And I cannot see through my kitty cat, but let's see. So that time it took less than 20 seconds, which is well within the minute time limit that Project Euler gives us, but the iron test is the answer right? And it is not. So, let's see. So my guess is we're probably counting some stuff more than once. I don't know that for certain, but that is my initial guess. I wonder. So I think something that I can do in Python is I can make a list very, very simply of all the numbers of interest. So I can do all nums is equal to, let's see, it would be list of range from 1 to limit plus 1, and then all non-abundant sums would be all nums minus sums of abundance. And what I think that will do is it will take all of the elements that are in this array and remove them from this array. And then we just go through this array and add that up. So let's see if that actually works the way that I think it will. And just do for... I'm going to call this non-abundant sum instead. That might also take a tad longer. We'll see. Okay, so we actually cannot subtract a list from a list in that manner. Okay. Let's see. So for A and sums of abundance, all nums dot remove A. And obviously, we're looping through a bunch of values a bunch of times. And that's not very efficient. Okay, we need to go back to removing our duplicates, I think. Let's see. Or we could just say if all non-abundant sums, or rather if A in, since this has an upper limit of that 28,123 values, it will be a lot smaller to search than this, which somehow got 12 million values. Obviously not really what we wanted. Okay, so it's probably this that is delaying us right now. Kind of want to see it go through. But it is taking over that minute mark, so obviously not the correct solution here. And I think probably this algorithm that I'm building up is just the wrong approach entirely. Like, I think this is good. But maybe there's no need to go find the sums of abundance. Maybe it's better to do something like this first. Okay, so that has all of that. And then instead of going through all of this, just like do this step in here as part of this other step. And we don't really need that step at all. Okay, let's see if that at least goes faster. Obviously, because we have this check back in here, it's taking a lot longer. Giving it another couple minutes just to see if it goes through at all. But I think it's relatively obvious that we're going to run over our time limit again. And that's no bueno. So let's see. I think that the logic we're going for is correct. And I also think that this is not what is slowing us down, because this always pops up really, really quickly. We could have it do the timestamp, then the output, just to make things more obvious. But I really don't think the sum of divisors is the slowdown here. I think it's checking whether the element is in the list. So what's a better way to build this out? Is there a good way to check that it is there? It's like there's these lists from a computer's perspective. We're working with a list that should never be greater than this 28,123 in size. And as you can see, there's only there's a little few less than 7,000 abundant numbers. So there should not be too many. We don't want to call sort a bunch of times because that would be inefficient. But maybe it would make sense to call it here. Yeah. Bring back maybe this part. Don't feel the need to keep printing out the last 10 of these. Okay, so we did actually get an answer there. It took 5 minutes instead of 1, so 5 times longer than our time limit. But this is an answer. I am tempted to go see if it is the correct answer, but let's see if I've made this even slightly more efficient. I feel like adding that sort in there, might make things a bit faster, but it also might not. So we'll have to just try it and see. I think, again, we'll find a huge slowdown with this second step. I think the, AN check is just inefficient in Python, perhaps. Maybe in other languages as well, similar checks are inefficient, I'm pretty certain. So let's see, instead of that... Yeah, this is actually a bad call. Okay, because if I just only add A's that are not between those two extremes, we don't know what those two extremes are, right? I mean, we do now, but we don't actually know what those extremes are. Um, so let's see. Let's do a little bitty Google real quick. You know what? Never mind. I don't actually want to Google it. I'm going to say sums of abundance is a dictionary now. I'm going to remove the sort. I'm going to remove this check. And I'm just going to say sums of abundance A is equal to 0. So let's see how quickly that gets through. Okay, so that's our... Okay, so this number actually matches this number that we got previously, where we finally got an answer different. I think. 4179871, 4179871, and I'm willing to bet that that answer is correct. Let's find out. And it is! There we go. So, correct answer. Time check took about 7 seconds. So, pretty good on that. Maybe 7.5, whatever. So the key here was using a dictionary as opposed to a list allowed us to effectively do the same thing as a set in Java, where now when we go through the A and sums of abundance, and actually, come to think of it, we could do this in kind of one step, and let's go ahead and do that. So instead of for A and sums of abundance, let's see, if not A in that, okay, so I did that pretty quickly. I'm going to go ahead and delete this since it did not work, or at least it did not work efficiently enough for us. Okay, so first we find all of our abundant numbers, then we find all of the sums of those numbers, then we go through all of the numbers, and actually I don't even need that anymore. And we say, if not A in sums of abundance, then we add it. Let's see if that works just as fast, if not faster. I expect it might be a little bit slower. Oh, well. Gotta use the correct variable name. Okay, so that, again, gave us that correct answer, and it actually was much more efficient. Probably because we were only looping through once instead of twice. So yeah, I think that is a good final answer, and I will catch you in the next one.